Well, hello there. Today we will be doing a topic on photoelectric effect. So this is a topic of A-level physics, and this is about the particle nature of light. So let's just get going. So before I get to photoelectric effect, I want to first tell you what is the meaning of photons. So light is considered to have dual nature. It can behave as a particle nature as well as it can behave as wave nature. So when it behaves like a particle, the particles of light are then known as photons. So photons are nothing but the particles of EM waves. Okay, light is not the keyword that your exam board accepts. So particles of EM waves. Now what do you mean by particles? You have understood that any electromagnetic wave is transverse, and it has energy distributed throughout it. It takes energy from one place to another. But now what we are learning, it has another nature, that this light wave is having particles in it, and these particles are known as photons. So just to understand the meaning, particles of light are known as photons. And now there's a lot of imagination here. So just try to have an open mind. So the particles, so it's like I'm assuming that the light coming out of my bulb in my bedroom is full of packets of energy, and these packets are known as photons. That's it. So particles of waves, particles of EM waves, particles of light are known as photons. And how much energy would each photon have would depend on the frequency of the light and the wavelength. Okay, so let's just move on to the next thing. Energy and wavelength of a photon. Energy of each photon is given by this equation, hc over lambda, or hf. F is the frequency, c is the speed of light, lambda is a wavelength, and h is something called as Planck's constant. This was given by a scientist called Planck. He is the one who came up with photon theory. So Planck's constant, and the value of this Planck's constant is I'm sorry. So the value of the Planck constant could be in terms of, as you can see, is it has E on the left hand side, so E is energy. So it can be in the form of joules, because joules is a unit of energy. And also I'll tell you today, you can also calculate energy in electron volts. So your H is both in joules as well as electron volts. So in joules, the value of H is H is 6.63 10 to the power minus 34 joules second. Okay, you don't need to remember this value, this is in the data sheet. And then in terms of electron volts, H is 4.14 10 to the power minus 15 electron volt seconds. Electron volt is another unit of energy. You don't need to know that right now. I'm going to explain where does it come from, but as of now, just the values. Okay, so as you can see, there's an orange color on your screen. So this orange color has a wavelength of around 600 nanometers. So this orange color has packets of energy in it, and each packet will have an energy of hc over lambda. So if I plug in the value of the constant, times nanometers, when you convert nanometers to meters, it is 10 to the power minus 9. Oops, this one is speed of light, 3 times 10 to the power 8. And wavelength is in denominator, 600 times 10 to the power minus 9. So when you solve this using a calculator, I'm just doing that, give me 1 second. So if I plug in, I'm getting it around 3 point something 10 to the power 3.3 times 10 to the power minus 17 joules. So each photon of orange light, wherever you see, will have this much energy, 3.3 times 10 to the power minus 17 joules. So everywhere, wherever you see, the photon of orange color would have this much. But how many photons would the orange color have? The number of photons would depend on whether your orange color is very bright or it's a dull orange color. So that depends on the intensity of the orange light. Okay, so I'm going to just, the next page is used up. So remember, energy depends on wavelength or frequency. Okay, energy of each photon depends on wavelength or frequency, whereas the intensity, number of photons, okay, how many photons are emitted by the orange color is dependent on intensity. So if you have a 100-watt orange bulb, it will emit more photons than a 50-watt orange bulb. Okay, so far only thing you have to remember is that a photon energy depends on the wavelength or frequency, and larger the wavelength, less the energy, because lambda is in the denominator. So if you have, let's say, a violet light, a violet color photon would have more energy than an orange color photon, because the violet wavelength is less than orange. The second thing you need to know is the number of photons that are coming in a light falling on your face when you're standing in light depends on the intensity of the light. So if you're standing under a very strong intensity light, the number of photons falling on your face would be higher, but the energy that each photon has, that depends only on the wavelength. Okay, the next thing, electron volts is the unit of energy. Okay, unit of energy. Now, how do you convert electron volts to joules? So 1 electron volt is just plugging in the value of electron, the charge of electron, 10 to the power minus 19 joules. That's it. That's it. Okay, so 1 electron volt is, if you just plug in the value of electron, it gets converted into joules. You'll see sometimes 4.2 electron volt energy converted into joules. Pause the video and find out. You just need to do times it by this. If I use my calculator, 4.2 times 1.6, so I'm getting 6.72. I hope you got the same. So 6.72 10 to the power minus 19 joules. Okay, whenever you have to convert electron volts, and you have to, because electron volts is not the standard unit, the standard unit is joules. Now, photoelectric effect. First discovered, it was discovered only after there was an, we know what are photons. Okay, once it was understood that light can have particles, once the particle nature of light was understood, the photoelectric effect was explained. The explanation was first given by Einstein, and we just need to, what we need to know for our A-level exams is what causes a photoelectric effect, what can increase the photoelectric effect, and what property of light does photoelectric effect explains. It explains the particle nature of light. Okay, that light is nothing but at times can behave like particles. And what are the particles of light known as? They are known as photons. Okay, now let's just move on. Now, what is photoelectric effect? Now, try to see in this diagram. As you can see, a torch is being shown on a metal. This is a piece of metal. So if now imagine now, because remember, photoelectric effect is all about particle nature. So if this light has these packets of energy, what are these packets of energy? Photons. And all these packets will have same energy because they have same wavelength. Now, when these packets of energy fall on the metal surface, electrons come out and they start flowing in the circuit. So these electrons are called as photoelectrons, and this entire process is photoelectric effect. Now, what are the steps for photoelectric effect? First, light of suitable frequency. Now, why suitable? Why do I need suitable frequency? Is because each of my photon will have an energy which is given by hf. If the frequency is too low, the packet will have too less energy and it cannot execute photoelectric effect. I'll explain that in a minute. Light of suitable frequency falls on a metal surface. Okay, falls on a metal surface. So it has fallen, fine, and photoelectrons are emitted. That's it. That's your photoelectric effect. Now, what is it? Let's just understand that. Okay, let me just explain you what's happening here is the first. Okay, so what's happening is there is a light which is having suitable frequency. Now, why suitable frequency? Just trying to draw a diagram here. So this is a piece of metal. Okay, now this packet of energy which is in the light, photon, it has suitable frequency. That means it has suitable energy. Now this one photon goes and knocks off this electron. This electron which is bounded to the metal with bounded to metal. So if it is bounded, would it require some energy? What kind of energy it requires? That energy is called as work function. Okay, and we're going to use the symbol phi. This is called phi. So now, first, photon has enough energy, goes off and hits this electron. So it frees the electrons. Now electron is free to move around. So this electron starts coming out. While coming out of the metal, it collides with the other electrons, other atoms on the way, and loses its energy. If it does not collide with anything, let's say the electron was on the surface and this photon collides with this electron and the electron comes out. So this electron that comes out, it will come out with what energy? So let's say this was the photon energy is E, and out of E the phi was taken to break the bonds. What energy is left to the electron will be the kinetic energy, maximum kinetic energy of the electron. Now why maximum? Is because it can lose a part of that energy in collision with the other atoms and other electrons while coming out. Okay, now where does the phi comes from? Phi is dependent on the kind of metal you are using. Aluminium, you're using magnesium, you're using gold or copper or whatever. So phi depends on the metal. That's how strongly the electrons are bonded. E depends on the light which you have used, and it would be the energy of the photon. Kmax is the maximum possible kinetic energy of the electrons. Now we have a simple setup here. See now this. Okay, no, sorry, where's the setup? Here. So this is the setup here. So this incident light, okay, what's the condition? Suitable frequency, because if the frequency is not enough, your photon will not have energy enough to break the bonds of electron. So once this packet falls on this, the electron breaks the bond, comes out, and because this no, sorry, this should be positive and this should be negative. So what this positive then does is attracts all the electrons, and the electron starts moving to this positive plate, and the A shows how much current is flowing in the circuit. So with the help of the light, with the help of photons, you're creating electrons. That's why it's called photoelectric effect. Okay, now what are the different things your photoelectric effect depends on? For that, first let's just do this. Einstein's equation, the equation that we just calculated, K max, maximum kinetic energy of emitted electrons, is the energy of photon minus work function. That's it. Okay, you can write E as hf minus work function. Now imagine if the frequency is too low, so low that is just breaking the bond. If it is just breaking the bond and the kinetic energy is zero, there's no energy left to give it to the electron. Whatever energy the photon has been taken away to break the bonds. So now it does not have any energy, isn't it? It does not have any energy, so K max is 0. And I'm taking that, so if I write 0 equals to hf minus work function, so the frequency that you calculate from the work function is called threshold frequency. If you give any metal frequency less than this frequency, what would happen? If the energy is less than this energy, it will not be able to break the bonds. Will electron come out? No, it won't come out. So that's the threshold frequency, the minimum frequency at which electron will just break the bonds, and then you can just attract them by giving a positive potential. All right. Now, so minimum frequency is the threshold frequency. So threshold frequency is the minimum frequency. Now, let's just do one question here. 4 electrons are released when a monochromatic means single wavelength, with a photon of energy. So the energy of each photon is this much. Work function, now see, they've given the work function in electron volts. You need to first convert it into joules by multiplying it with the charge of electron, that is this. I'm just using my calculator. 2.4 times 1.6. So I am getting this 3.8 times 3.8 times 10 to the power minus 19. So this is the energy of the photon, out of which this much energy was used to break the bonds. How much energy is left? Energy left would be the K max. So K max would be 4.2 times 10 to the power minus 19. Take away 3.8 times 10 to the power minus 19, which is 0.4 times 10 to the power minus 19. So this much energy would be the maximum kinetic energy of any photoelectrons that's emitted. Now it's not interested in maximum kinetic energy, it's interested in the speed. So then you use half mv square equals to this and find the v. So what's the mass? Mass is 9.1, so I'm just going to do that. 0.4 times 2 divided by 9.1 times 10 to the power. So I'm getting around 2.9. So the answer would be C. So whatever energy is the photon energy, that can be used in two ways. One to break the bonds, work function, one to give the kinetic energy. Now, what kind of graphs you require for your A-level physics? In this, the first graph would be between kinetic energy and the frequency. Okay, the graph between the maximum kinetic energy of the emitted electrons and the frequency of incident light. So I'm just going to make a diagram here. So this is your metal plate. If the incident light, when you increase the frequency, what happened to HF? Increases. HF increases means HF minus work function would also increase. So this is the equation for my Ke max, isn't it? So if I compare it to y equals to mx plus c, it has a negative intercept. So somewhere here, oops, that would be my graph, a straight line. And this point where the kinetic energy is 0, that gives you the threshold frequency. I'm just using the symbol F0 for threshold frequency. What is the threshold frequency? It's the minimum frequency at which the maximum kinetic energy is 0. So there's no all of the energy is used up for the breaking the bonds. Okay, and obviously there's nothing as negative kinetic energy, so we're going to get rid of this and just use that to explain that this would be a negative intercept. So that would be, so if I increase the frequency, if I show you two more graphs here, let's say if I have this graph, okay, all of these lines are showing that the threshold frequency is increasing. That means there must be three different metals. So metal 1, metal 2, metal 3. Exam question, which of them has higher threshold frequency? So 3 would have higher threshold frequency. Okay, another kind of graph. So another kind of graph would be, suppose if I am increasing the intensity of the light. Okay, this is where it tells me. So if I increase the intensity, so I'm just taking intensity. So if I take intensity, I'm just changing the intensity of the light without changing the frequency. What would happen? Nothing would happen, because intensity just increases. Intensity means the number of photons would increase. But will each packet have more energy? No, because the frequency is not changing. So the frequency is not changing. Will K max change? No, so the intensity changes, but the K max would remain constant. It would not change. So do you see? So you have to understand what it is trying to say. We'll be doing some exam questions where different kinds of graph are asked, but understand what each graph is explaining you. Another kind of graph which comes is on stopping potential. So see here. Now if I make this as negative and I make this positive, okay, so this plate becomes negative. Now what is this plate trying to do is, it is trying to stop the electrons. So what is this? So that voltage which stops the most, I need some space to write. Okay, I'm just going to write it here. So now stopping potential is that negative voltage. Stopping potential, the negative voltage. Now you're giving negative voltage. Why are you giving negative potential? To stop the electron. Which electron do you want to stop? Which electron will stop last? the electron with the largest kinetic energy. So the negative potential required to stop the most energetic electron. Okay, the most energetic electron. That is the stopping potential. Okay, so now the most energetic electron has Ke max. So if this has become equals to EV naught, where V naught is a stopping potential, so then the electron stops. So if I have, let's say, two electrons here, the one which has the maximum kinetic energy, this one, if I can stop this, obviously the other ones will automatically stop. So I have to stop the maximum energy. So I keep on changing this voltage. So at 1 voltage, my maximum energy electron stops. So that voltage is given by this. Ke max is EV naught. Okay, so at the what voltage? At the negative voltage at which the maximum energy electron stops is the stopping voltage. Now what it does is, if I draw a graph between stopping potential, so if I draw the graph between stopping potential and, let's say, frequency. Okay, now what would happen when you increase the frequency? When I increase this frequency, the kinetic energy increases, so obviously the stopping potential will also increase, right? But when stopping potential is 0, oops, okay, so if I am, so then that, let me just do one thing. Let me just take so if I'm increasing the frequency, is my stopping potential increasing? Yes. So again, I'll have the similar graph as kinetic energy, because V0 is nothing but Ke. Only thing is, it'll have a different gradient. Okay, so my EV naught, which is Ke max, will be equal to HF minus work function. So my V naught will be HF divided by E. So my gradient would be H over E. Alright, so different graphs would have different gradient, different intercept depending on what it is given. Just try to read the graph, spend a minute or two with the given graph, understand what's on the y-axis, what's on the x-axis, what kind of equation is being used, and then you'll be able to figure out. Okay, let's read this question. Ideally, pause the video and you try to do it yourself, and then check the answer with me. Photoelectricity, Vs is a stopping potential, so they have taken Vs. What quantity is EVs then? So when you multiply V with E, it gives energy. But which energy? Maximum kinetic energy of photoelectron. Okay, let's see. A current is measured on the microammeter when an electromagnetic radiation with a frequency greater than a certain value is incident. Fine. If it is not, say what we're doing here is we're doing a light ray being incident. Explain why the frequency must be greater than a certain value. Okay, because what does a photon has to do? It has to break the bond. Okay, so HF should be greater than work function, so that HF minus work function can give it Ke, which is Ke max. So why the frequency of EM radiation should be greater? So that it can break the bonds. Okay, see, so that's the answer. So frequency should be related to energy. Every photon will have a minimum energy, which is given by E equals to HF, and then there is a minimum energy required to break the bonds and then remove the photoelectrons. Let's do this one. Now, every time you have a question on the graph, first take a second to understand what the graph is all about. So this graph is between the photoelectric current I in microamperes and voltage. As the voltage is made negative, 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 at some point the current has become zero. That means it is the stopping potential that has stopped all the electrons. Determine the number of photoelectrons per second leaving the surface when the current is maximum. What's the current? The current is maximum somewhere here. Okay, so what is the maximum current? 30 microamps. So 30 times 10 to the power minus 6 is the current. Number of photoelectrons per second. Now remember, did you remember current is charge per second, rate of change of charge? Okay, and time is given as 1 second, and this you can write as NE. Q is NE, time is 1, so 30 divided times 10 to the power minus 6 divided by the charge of electron is then N. Okay, so that is coming as 30 divided by 1.6. So I'm getting approximately 18.75 10 to the power 13 electrons. Explain why I reaches a constant value for positive value of V. So why has current become constant? So current has become constant because the number of electrons that were emitted. I'm going to go back to this diagram. So what would happen? As you increase the voltage, okay, it is attracting the electrons. It is attracting the electrons with 0 energy, with 0.5, with 1, all the way up to the maximum energy, so Ke max. So once it has attracted all the electrons with the highest or the lowest possible energy also, there's no more electron left to attract. So the current will become constant. So as you increase the voltage, as the voltage is increased, which electron is being attracted here? The maximum energy, because it already has maximum energy. So small 0 volts also attracts it. It comes a little bit more voltage, a higher energy electron is attracted. More energy, and at this point even the 0 energy electron has been attracted. No more electrons to attract, so hence the current becomes constant. Okay, so for the second mark, so the first mark is when you explain that all the electrons had been collected, even the 0 energy electron has been collected, so the current becomes constant. The second mark would be as the intensity of the light is not changing, that means the number of photons are not changing, so the number of electrons are not changing. It's like for each collision between photon and electron, U's number of photons are not changing because the intensity is not changing. Okay, let's check the answer. So number of photoelectrons depends on the intensity. We talked about that. And the constant current reached when all photoelectrons are collected or reached a node due to positive potential. It has collected or even the 0 energy electron. Let's do this one. An isolated metal plate is given a negative charge. Okay, electromagnetic radiations are incident on this plate. The plate loses its charge due to photoelectric effect. How the rate of loss of charge from the plate depends on the frequency. Larger the frequency, larger the energy. Okay, so frequency decides the size of the energy and intensity decides the number of the photons. Okay, so if you increase the intensity, you end up increases the number of photon, and hence the number of electrons would increase if the energy of each packet is higher than the energy of work function. Okay, so you should explain why the place loses charge. Why would the place lose its charge? Because photoelectrons are emitted. So I'm going to explain point by point. Photoelectrons are emitted. Why are they emitted? Because frequency is, or energy of each photon is higher than what? Is higher than work function. Okay, so it is emitted. So point number 1, explain, 2 marks. Point number 2, photoelectric effect occurs when the frequency is greater than, so you have kind of explained that also, because the number of the energy of each photon is higher than the work function, so the electrons are being emitted out. And as the intensity increases, I'm talking about the third point now, intensity increases, the number of photons increases. Okay, so now number of photons have increased, so now each photon is going to collide with more electrons, so number of electrons, I'm writing some short forms, just bear with me, I don't want to bore you with the writing speed, that's why. Number of electrons increases with increased number of photons, and when the photons have increased, the number of electrons increases and the rate of loss of charge increases. Okay, now just to add more marks, I don't think this is going to get us 6 marks. We have also to explain that how does the plate loses its charge. Okay, we have not explained how loses its charge, because the electrons are emitted, it loses its charge. Yes, we have explained. So because it is emitting out electrons, and then we explain the frequency. Let's just check the mark scheme. Loses charge, we explained why it loses charge, because of emission of electrons from the surface. Photoelectrons are emitted. Did we write emitted? Yes, so emitted, so that gets the first mark. Then this increases or number of time, then okay, the photoelectric effect and the frequency. So second area B, minimum energy required, work function, we have talked about that. A photon must supply this energy. Yes, we could have added that, but then we have explained that energy of a photon is directly proportional to frequency. Minimum frequency is threshold frequency. Did we write that? Okay, we could have added that. We could have written energy of each photon is HF. That would have given it 1 more marks. Yeah, okay. All right. Then last point is when you talk about the intensity, intensity results in more photons. We have written that. The mass increase the number of photons, frequency increases. Yes, we have written that. Okay, so this is kind of like explaining what photoelectric effect all about is. I've just written in the last 2 seconds, I've just summarized it. So what you can do is you can pause and go through it, and I also wanted to show you a simulation to explain you once again. Just bear with me. Just bear with me. Right, I hope you can see the screen. So just what I wanted to show you here is how the negative potential and the positive potential happens. So what are we going to do is I'm going to show you that at this wavelength, so the target is sodium, so this is this small strip here, you can see is a sodium. I don't know if my pen, it is going to allow my pen to write now. It's not letting me, but I hope, can you see my arrow as I'm moving it? Hoping yes. Okay, now let's see. So there's no current, 0 0. You can see the voltage is 0. So once I increase the voltage, nothing happening, no current, okay, because the circuit is not completed. So I am going to increase the voltage to 0 0, and I'm increasing light intensity. Okay, so there was no photons. Okay, if my intensity is 0, there's no photons. If I increase the intensity to 8%, see how many electrons are coming out. There are 2 electrons. So this one is the fastest. The first one is obviously the fastest, Ke max, less Ke here. Now, now see, still 2. Now what I'm increasing is, I'm increasing the intensity. Let's see what happens then. More photons are coming in. So more electrons starts coming out. Okay, more photons, more electrons. Now I am now increasing the wavelength. Increasing wavelength means I'm decreasing the frequency. So energy is decreasing. Okay, see? The electrons have almost become 0. So even if I increase my intensity, nothing is happening. So 100% intensity, but not even a single electron. Why? Because now the photons of my green light, they do not have sufficient frequency or sufficient energy to break the bonds of electrons. Okay, let's just see current versus intensity graph. Say I'm just going to have a current first. So my current is there, and I'm going to vary the intensity. Okay, let's see. As the intensity increases, the current increases. Yeah, you can see here 0.1133. So because the intensity means more photons, hence more electrons, but provided each photon should have that minimum frequency. If it doesn't have, even if the intensity is high, if I decrease the frequency, the current is 0. There's no current. Doesn't matter. Intensity is so high. See, intensity is here, but the current is still 0. Okay, now what we're going to do is we're going to measure electron energy. So we are going to take high energy. Less wavelength means high energy. Let me show you this graph. Okay, so frequency and energy. I'm increasing the frequency, so you can see the energy is increasing. Decreasing wavelength means increasing frequency. Now I'm just going to go other way around so that it meets. So the 0 energy is happening at around this frequency, 486 nanometers. You can calculate that. Now I want to show you the current versus battery voltage. Okay, so the current is there because a large number of electrons are being emitted. But if I make this potential higher, it is going to attract the electrons quicker. Is the current increasing? Why is this not increasing? Let's just decrease the frequency. So see. Yeah. So larger current, larger voltage means larger current. I'm going to further decrease it. Okay, let's just try this again. Now see, my current is increasing as I increase my voltage, but it has become constant. Why has it become constant? Because it has attracted even the lowest energy electron. So the current has become constant. But if I make my voltage negative, now it is trying to stop it. The minute even the maximum energy electron is stopped, that's when the current becomes 0. All right. So see, now it's not letting even the highest energy electron is somewhere here. It's not letting even that one come here. So this one, the closest to the plate, is highest energy. Stop that. So the stopping potential with this one would be like, I don't know, it has stopped here, right? So -2. So -2 is the stopping potential for sodium for this wavelength. Okay, I hope we got it. So if you have anything you're not clear, rewind the video and see the simulation. And this is a difficult topic, it's a very confusing topic, so practice more and more questions and merit minds. Hopefully that would clear the concepts. And We'll see you soon. Thank you. Bye bye.